हेलो बच्चों, सत श्री अकाल and namaste from my side. How are you all? Right? Are you all fine? Yes or no? Are you all fine? Okay. So nice. Again, welcoming you all to the recap batch. Okay, this is your own physics educator Indrajit Singh. Right? Welcoming you all into the most awesome batch. Allow me to set up my mic. Okay. Right. As usual, you all are aware that today we are going to start with the alternating current and we are going to follow the reverse engineering. All the time I used to say into the lectures that we are going to follow the reverse engineering. We are going to follow the reverse engineering, and same we are going to do so. Okay, same we are going to do so. Okay, reverse engineering. Why the reverse engineering is bit popular? Because through PYQs, through questions, we are able to understand the theory of the entire chapter. And that is the most awesome part. So I think let's, without wasting our time, let's move on to that part. Okay. So today we are going to solve the PYQs, and through PYQs, the theories of the alternating current. Right. So the agenda of today's lecture will be what? Practice questions. Okay. Basically the PYQs. Okay. So guys, let's move on to it. Right. Let's move on to the first question. In an AC circuit, the instantaneous EMF and the current are given by. First of all, I want to tell you all this question is asked in JEE Main 2018. Right. This question is asked in JEE Main 2018. Right. Okay. So in an AC circuit, the instantaneous EMF and current are given by. This is the equation of the instantaneous EMF and this is the equation of the instantaneous current. Now, in one cycle of the alternating current, the average power consumed by the circuit and wattless current will be what? Average power consumed by the circuit and the wattless current. Okay. So what is the data given? First of all, just check it out. Whatever the data it is given, the data it is given as equation of the EMF, that is equal to 100 sine of 30t, right? Equation of the current is 20 sine of 30t minus pi by 4, right? That is the data given. What we need to calculate? We need to calculate the average power consumed into the circuit. Right, it will be what, and what will be the wattless current? I told you all into the previous lecture, right? Okay, I told you all into the previous lecture, the maximum number of the questions are going to come upon from the Q factor, power factor, wattless current, and LRC series circuit. So this is an agenda. Okay, so now I think we should all give you a minute. Okay, come on, try to solve an answer. I'm moving aside. Less than half minute is remaining. Come on, everyone. First of all, it reminds us about the very simple formula, right? What we need to calculate, the data given is this, and we need to calculate, we need to evaluate this part. Okay, so obviously we need to find out the bridge, Okay, first of all, what is the formula of the average power consumed into the circuit, right? The formula, here I am going to write down the formulas of the average power consumed into the circuit, that is going to be VRMS, right? RMS cos of phi. VRMS, IRMS cos of phi. Here, if you are analyzing the equation of the voltages and current, the phase difference between the voltages and current is pi by 4. Yeah, I can understand it is the current is lagging. You can see this equation. The current is lagging the voltages by pi by 4. Right? But the phase difference between the two vectors is somewhat, we can say, just hold on. Yes. Okay. We can say that, okay, it is like, this is the EMF, right? This is the current. The phase difference between them is pi by 4, and they both are rotating into the anti-clockwise direction. They both are rotating into the anti-clockwise direction, right? So here what happens? The average power consumed into the circuit. First of all, the phase difference between them is pi by 4. So can I say the phi is the angle? Here in this formula, the phi is the angle between VRMS and IRM, or you can say this voltages and the current. And that is nothing else but the pi by 4. Okay. So replacing the values, okay, now, can I replace VRMS as V0 by root 2? I naught by root 2 cos of phi. What is V naught? From the equation, the voltage amplitude is 100. Okay, so I am replacing it is 100 by root 2. Okay, from the equation of the current, the peak value is 20 into 20 by root 2 cos of pi by 4. Right, cos of pi by 4. So here it is going to be 100 into 20 by root 2. Okay. So this is going to be 100 into 20 whole divided by cos pi by 4 is 2 root 2. So it's 2 tens are, this is equivalent to 1000 by root 2. The average power consumed, that will be equivalent to 1000 by root 2 watt. Okay. Now, many students will be have a click. Sir, we have already found this average power, right? No other than C option is there, right? So, in that case, please rectify your answer once. Okay, just check it out whether you have done right or wrong. Okay, you have to just check it out whether you have done right or wrong. Okay, you have to check it out. Okay, so average power consumed into the circuit is now, what will be the wattless current? Okay, I told you all, see, if I am talking about the current, okay, this is the phase difference, right? This is a 45 degree, then we are having the two components. This one is I cos of 45, right? Okay, this one is I, right, sine of 45. The wattless current is always I sine of 45, right? So this will be equivalent to I naught by root 2. This is going to be the RMS. So we have to convert it into the peak. That is 1 by root 2. I naught value is nothing else but the 20 by 2. So the wattless current, it is going to be 10 ampere, right? Wattless current, it is going to be the 10 ampere. The C will be the perfect answer for this specific question. Okay, the C will be the perfect answer for this specific question. Okay, I am moving aside, and some students might be thinking, sir, why you solve like this way? The same thing is going into your examination. You will be having the paper, and beneath the paper you will be having the space, right? Okay, so whatever the calculations you have to do, half of the calculations you have to do by your own, by heart, right? And immediately the needed stuff you are going to write on the paper. Okay, everything you are not going to write on the paper. If you are going to do that, then half of the minute is you are going to consume in rubbing it up. Okay, so moving aside, you can just note it down whatever you want to. Okay, else we can move forward to the next question. Okay, a very nice question that was asked from like JEE Main 2018, the average power consumed and the wattless current. Now here, suppose if they are calculating, they are asking, right, what will be the watt full current? Then this will be the watt full, I cos 45. Okay. Hope so you might have paused up this video and moved. Let's move on to the next. Again, the question that is asked in JEE Main 2018. For an RLC circuit driven with the voltage of amplitude Vm. See, here again came upon RLC circuit, right? RLC circuit with the voltage amplitude of Vm and the frequency omega naught, that is 1 by under root of LC. Then we need to calculate the quality factor, the recent question that has been asked on the quality factor. Okay. Again, I am going to tell you all after 2018, okay. Again in 2021 question came on the quality factor. In 2021, the question came on the quality factor. In 2020, the question came like, they gave you all the 4 options. In 2020, B, C, and D. Sorry, in 2021. I'm sorry, 2021. They gave you all the 4 options. They gave you the different value of L, R, and C, right? Okay. Now they in the question it was written, these are the some specific set of the values, and we want to construct the LCR series circuit, right? We want to construct the LCR series circuit. Okay, so in that case, what happens? Which combination would give the maximum output? Indirectly, they were directing you all towards the power factor, sorry, quality factor. Okay, so this was asked into the question. This question was asked in 2000. Right now, the data it is given as angular frequency, it is equivalent to 1 by under root of LC. Okay, this only happens into the resonance situation. This is a resonant frequency. We need to find out the quality factor, right? Okay, so this is the data given. This is the output we needed. Okay. I heartily apologize for that. Sorry. It's a very easy question. You can solve within a span of the 15 seconds. Okay, simple. The data given into the question, is all about the resonant frequency is omega naught under root of 1 by under root of LC. The quality factor we need to calculate. Okay. Into the previous lecture, I told you all about the formula of the quality factor, right? It reminds us the quality factor is nothing else 1 by R under root of L by C. The nicest, the greater value of the quality factor will give you, right, the maximum output. Your circuit is well connected with the appropriate values. right? Okay. Now, here what happens? Can I consider this as equation number 1? Okay. Now, can I say omega under root of L, that is equal to 1 by under root of C? Can I consider this as equation number 2? Can I replace equation 2 in equation number 1? Okay. So here, replacing 2 in 1, right? Replacing 2 in 1. What we get? Q, that is equal to 1 by R under root of L by C. Okay. So I am replacing 1 by L. Okay. The quality factor, it is going to come upon as omega naught L by R. Okay. Omega naught L by R. Okay. The B will be the perfect answer for this specific question. Right. B will be the perfect answer for this specific question. Yes or no, guys? B will be the perfect answer for this specific question. I'm moving aside. You can just pause this video in the countdown of 10 seconds. We are moving forward to the next question. Come on, everyone. If you just note it down, you can. It's 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. An arc lamp requires a direct current of 10 ampere at 80 volt. Now this question shows the comparison between the DC circuit and the AC circuit. The question that was asked in JEE Mains 2016, please don't worry, from this chapter direct formula based questions are going to come. This is not a matter that you are getting worried. Just formula based questions are going to come. Okay, so just enjoy. An arc lamp requires a direct current of 10 ampere at 80 volt. Okay. Now suppose the same thing is connected to the alternating supply of 20 to 20 RMS and 50 Hertz frequency. What will be the value of the inductor that is connected in series with the resistor? What will be its value for it to the work is close to? In both of these circuits, the work done is close, nearer equivalent to each other. So here, first of all, I want to give you all what actual the data it is given. One side, right, the DC circuit is given. Second side, the AC circuit is given. Here only resistor we are having, right? Okay. Now in this current flown into the circuit, it is given as how much? 10 ampere, right? The voltage connected, the DC voltage connected, it is given as 80 volt. This is a part of the DC circuit. Now same thing happens into the AC, but with the resistor in series, the inductor is also connected. Okay, it is constantly given the alternating supply. Now data regarding the supply, it is given 220 VRMS value. Okay, and the 50 Hertz of frequency is there. Right. Here the value of the resistance is R, here the value of the resistance is R, here the value of the inductor is same. Now in both of the circuits they are saying, right, in both of the circuits they are saying, right, the voltages are the work done is nearly close to each other. Okay, what we need to calculate the value of the inductance in it. Okay, so let's give you all a minute to solve this question. Right now, it's a very simple thing. First of all, we are going to calculate this. In both of the circuits, the value of the R is needed to evaluate. So first of all, from the DC circuit, using the Ohm's law, we are going to calculate the value of R. Okay. So the first step, using Ohm's law, right, the value of the R, that will be V by I, that is going to be 8 ohm. Okay. Now successfully we calculated the value of the R. Now second step would be what? Okay. Here it is an RL circuit. Okay. It is what? RL circuit. So in RL circuit, what happens? The value of the impedance, it would be R square plus omega square L square. R square plus omega square L square. This will be the resultant impedance. Okay. Now the VRMS voltages are given. Okay. Okay. Now what we need to calculate? Okay. The value of the direct current, that will be equivalent to 10 ampere. Okay. So here can we write it out as we can write it down now. Okay, what will be the VRMS value? 220 volt. What will be the value of the RMS value of the current? You see, in both of the cases, work done is close. So this can be only possible when the current flowing in both of them will be same, right? Okay. So impedance, that would be under root of R square. What is the value of the R? 8 square plus what is omega? 50 hertz it is there na. So let's say it is 2 pi f, right, into L whole square. Okay. So finally we are going to say 22, that is equal to under root of 8 square plus, okay, frequency is 50 hertz. So 2 pi into 50, 100 pi. Okay. So it is 100 pi L whole square. So this is 22 square is equal to 8 square plus, right, 100, it is 10 to the power 4 pi square into L square. Pi square is nearly equivalent to 10. So it's 22 square minus 8 square is equal to 10 to the power 5 into L square. So L square, that is equal to 22 square minus 8 square whole divided by 10 to the power 5. Okay. So your answer is nearly about 22 square. Okay. So it means that 400. Okay. 64 by. Nearly about it is going to be 0.065 Henry, right? Nearly about it is going to be 0.065 Henry. Okay, the D is the perfect answer for this specific question. Okay, I'm moving aside. If you just note this down, you can, right? D will be the perfect answer for this specific question. On the countdown of 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. The phase difference between the alternating current and the EMF is pi by 2. Phase difference between the alternating current and the EMF. The EMF and the current is pi by 2. Which of the following cannot be the constituent of the circuit? Which of the following cannot be the constituent of the circuit? It means that through which combination this situation is not possible. Suppose if only the circuit only contains L. Right. So is it possible? Suppose the circuit contains L and C in series. Is it possible? Suppose the circuit contains R and L in series. Is it possible? Suppose the circuit contains only capacitance. Is it possible? Right. So the question is asked from AIEEE 2005. Among all of those 4 combinations, we have to select the correct one through which the phase difference between the alternating and EMF, alternating current and EMF as pi by 2 is not possible. Giving you all a minute to solve this stuff. Come on, everyone. Right. The phase difference between the alternating current. See, मैंने we moved on. Tan phi, that is equal to XL minus XC whole divided by R. This formula we have seen into the phasor, right? Okay. How it obtained? This was XL minus XC. This was R. Somewhere this was a resultant, and this was the angle that a resultant was making, okay, with the R, with the positive x-axis. This thing we have seen into the phasor. Using this formula, okay, using this formula and trial and error method, we are going to select the correct option. So many students might be thinking, what actually is the trial and error method? It's not like that. Trial and error method states that each option given should be analyzed with the question data. Each an option given should be analyzed with the question data such that you have to reach up to the answers. Right? We have to reach up to the answer. So what happens here? Right? What happens here? Okay. First, I'm going to select the option number A, the circuit that only contains the inductor. Okay. If it reminds about the formula tan phi, that is nothing else. Okay, this is a tan phi, and this is an angle between that one. This is a 90 degree. Okay. So let's say tan phi XL minus XC whole divided by R. So can I say we are having the XL by 0, right? So the value is going to be infinity, right? So if the circuit that contains only inductor, if you want to plot up this phasor, right? Okay, then this will be the current, right? This will be the EMF, right? There can be the phase difference between the current and EMF as pi by 2. This thing we have seen into the phasor. So here it means that L, if you are using the inductor alone into the circuit, there is a highest possibility for a phase difference between the current and EMF to be pi by 2. Okay, so I have rejected this answer. Okay. Second is L and C. Let's check it out using trial and error method. Let's check it out, the second option. Suppose the series, the circuit contains L and C. Again C. Tan phi, that is equal to XL minus XC. No resistor is 0. So here again tan phi, okay, that extends to infinity. Okay. So I must say here it is XL minus XC, and this will be EMF. Again, the phase difference between them 90 degrees possible. If the circuit contains L and C, there is the possibility for the phase difference to between the EMF and the current to be pi by 2. Where, okay, fourth option, the C alone. In C alone, it is also possible. Why? Because we have seen the phasor diagram for the C circuit, right? This will be the value of current, this will be the value of EMF, angle between them is 90 degrees. So it is possible, right? So this, with this combination also we can't create a circuit in which, right, the phase difference shouldn't be pi by 2. Where there is a R, things are going to get weird, right? Where we are having R, things are going to get weird. Actually, here the option should be R alone. R alone is the most accurate answer through which we can create a circuit in which the EMF, the phase difference between the EMF and the current can't be pi by 2, because if the circuit that only contains R, the V and I are always overlapping each other. If the circuit that contains only R, V and I always overlap each other, right? But suppose even the circuit contains L and R, where there is a R, the phase difference can't be pi by 2, right? The phase difference can't be pi by 2, right? So here right now the C will be the perfect answer. Actually it should be R alone. In some of the resources it is given as R alone, right? But right now as comparing all of those options, the remaining one is the third one, okay, by trial and error method, and the nearest is also third one, not the accurate, but the nearest is one. Accurate should be R alone, okay? So yeah, the C is the perfect answer for this specific question. I'm moving aside. If you want to just note this down, you can. Okay, I think that much time is enough. Okay, let's move on to the next question. In a circuit resonant LCR, voltage across the R is 100 volt. Write down the data. Voltage across the R is 100 volt. Resistance is given as 1 kilo ohm. Right. Value of the capacitance is given as 2 microfarad. The question is asked in AIEEE 2006. The resonance frequency, it is given as omega is equal to 200 radian per second. In the resonance condition, what will be the voltage across the inductor? Very nice question. In the resonance condition, what will be the voltage across the inductor? Okay, first of all, let's create out a circuit, right? Without circuit, it is impossible to find out all of those things, right? Okay, the circuit is somewhat like this way. Okay. Now where the value of the R, it is given as 1 kilo ohm, right? The inductance value is not given. The capacitance is given as 2 microfarad. Okay. Omega value, it is given as 200 radian per second. And the voltage across the L, it is given, sorry, the voltage across the R, right? It is given as how much? 100 volt. We need to calculate the voltage across the L. So it's a very simple. The circuit is in resonance. Okay. We are not aware of what actual the value of the L is all about. First thing, if the circuit is in resonance, it means that omega L is equivalent to 1 by omega C. XL is equivalent to XC. This was the term that I used into the previous lecture to explain you all what actual the resonance is all about. Right. So here the L is going to be 1 by omega square. What is the omega? It's 200 into 200. What is the value of C? 2 into 10 to the power minus 6. The L, it is going to be 0.125 into 10 to the power 2. The L, it is going to be 12.5 Henry. First step successfully completed. The value of the inductance of the circuit, the inductor that has been connected to the circuit, we got is as 12.5 Henry. Now, the second step would be, we need to calculate the value of voltage across the circuit. So can I voltage across the inductance, VL. So can I say the voltage across the inductance, that is current that is flowing into the circuit into omega L. Very simple. So the current that is flowing, see now the circuit is in resonance condition. So it means it is a purely resistive circuit. Purely resistive circuit. Okay. So whatever the voltage across the R, it is only the VRMS given to the circuit. Why? It is into the resonance, right? Okay, it is into the resonance. So we can say it is like, okay. Or you can say, not voltages, but the current flowing. Okay, I'm sorry for that. That is 100, okay, whole divided by 1 kilo ohm, that is 10 to the power 3 into 200 into 12.5, right? So the voltage across this, it is going to be approximately equivalent to, okay, 250 volt. Okay. A is the perfect answer for this specific question. A is the perfect answer for this specific question. Right? A is the perfect answer for this specific question. I'm moving aside. If you just note this down, you can note this. It's not a big deal. Okay, that's it. Let's move on to the next question. In an AC circuit, the voltage applied is E naught sine of omega t. This is the equation of the voltage supplied to the circuit. The resultant current, it is given as I naught is equal to I naught omega t minus pi by 2. This is a very simple question asked in right EIEEE 2007. The average power or the power consumption into the circuit, it is given as a very simple question. Directly you can select this part, right? Okay. If you can see this equation part, the EMF is this, the current is this, right? If I'm drawing up the phasor, okay, if I'm going to draw the phasor, then this will be the E naught and this will be the I naught, the phase difference them between pi by 2, right? They both are rotating with the angular velocity omega, but here the voltage leads the current by the pi by 2, and this only happens into the L circuit. I'm taking one of the, I'm not saying it only happens into the L circuit, right? But this is only the example that we are having right now, we are having in front to understand this concept. Okay, so in that, power is 0. Right? Power is 0. Because if there is a phase difference, okay, and we are about to calculate the power, right? Then how we are going to do that? The average power, it is going to be integration, right, of what? VRMS IRMS, right? Or you can say that VI cos of phi. So let's say this as okay, V naught sine of omega t I naught, right? Sorry, I forgot to write it here, sine. Okay, sine of omega t minus pi by 2. This is 90 degree, right? So we have to evaluate this t2 minus t1. So p into delta t, that is equal to integration of sine of omega t I naught sine of omega t minus pi by 2, right? Integration will move on from 0 to t, and obviously if I'm going to convert sine to cos, things are going to be 0. So the average power consumed is going to be 0. The first is a perfect answer for this specific, right? And this thing obviously we have seen theoretically. Now, the power factor of the AC circuit is this. Okay, this is a very easy question. So I'm giving you all into the homework from my side, right? The question is asked in EIEEE 2022. Now the important stuff is transformer. What is a transformer? We are going to have the detailed discussion of it regarding the transformer. Again, we are going to solve this question. So first of all, what is the main purpose of the transformer? And working of it. It reminds me about the history. Thomas Alva Edison, okay, was a most powerful person who gave a rise, right, who placed the advancements into the field of electromagnetism. Electricity. At that time only the DC was there. Okay, as a rival, we were having Tesla, right? Tesla believes in AC. Okay, Thomas Alva Edison believes in DC. So at that time, the major issue was going on to transfer the current from one place to another place, right? Lots of poles were needed. And at that moment of time, it was quite expensive. No doubt, Thomas Alva Edison was a great personality and he discovered, right? He gave us a light into our life, but that light was quite expensive and it was quite difficult to transfer that from the electricity from one point to the very large distances. So at that point of time, Tesla came up with an idea, right? Transformer, right? Okay. Now what was this? Generally, transformer is like that. Okay. Indirectly using the transformer, right? You can step up and step down the source voltages so that it can transfer up to the long distances. This wasn't the tool through which, right, the current was transferred. No, this was the initial step in which the voltages were lowered down and were transferred. Okay, how? Which factors were varying, which factors weren't? We are going to see. So the transformer was having that kind of this. See, basically transformer was having the two coils. One side we are having the primary coil. Second side we are having the secondary coil. Right. The primary source is connected to the alternating supply. On the opposite side, we are getting the output voltages. This is what the transformer is all about. Now see, the most important stuff, which thing is getting changed, right? How? Lots of things we are going to see. The first step, okay? The main thing about the transformer is primary coil, the supply voltages are given. Now, as this supply voltages are alternating, the supply is alternating, as because of that the current is alternating. Current is alternating, as because of that the current is changing. As because of that, right, there is a change in the value of the magnetic field. If the value of the magnetic field get changed, the flux is getting changed. This we have seen into the previous chapter of EMI. So as because of that, here whatever the change in EMF was there, it was about to create one induced EMF into the opposite coil. Whatever the change in flux, whatever the change in flux of the primary coil was there, it was about to create, right, it was creating another, right, okay, self, I can't say self, but induced EMF into the opposite coil. Current was changing, magnetic field changes, right, flux changes. As because of this change into the flux, what happens, right, EMF is induced into the secondary coil. Now, here voltages were varying, current was varying on the both side. Voltage was varying, current was varying, voltage was varying, current was varying, but on both of the coils one thing was the common, that is frequency of them. Frequency never changes into the transformer. Frequency was common in between the two coils, right? Frequency was common in between the two coils. Okay, so here voltage changes, current is getting changed, magnetic field changes around it, right? As because see here, there was a change into the magnetic field like this way. Okay, so as because of the change in this magnetic field, induced EMF, the flux is getting changed, and according to the Faraday's law, EMF is induced into the opposite coil. Right, so this is the main function. Voltage and current varies, as because of this change into the voltages and the current, right, the EMF is getting induced into the opposite coil. But here VI changes, frequency remains constant. This is the main function and the working of the transformer. It is nothing else but the Faraday's law. Now, two types of transformers are there, step up and step down. On the primary side, low voltages are there. If you want to step up, this is a step up. If you want to step down, increase the number of the turns onto the primary coil and decrease the number of the turns into the secondary coil. Okay, so these are the number of the turns of the coil on the primary side. These are the number of the turns of the coil into the secondary side. Now, I'm going to show you all again. Step up and step down. Step up. Step down. Right? Step up, step down. Now what actually happens? It is based on the Faraday's law of electromagnetic induction. On the primary side, whatever the EMF is that, it is as because of the number of the terms on the primary side and flux is getting changed. Similarly, on the C, this is a primary coil and this is a secondary coil. Okay, on the secondary side, we are having negative of N of P, that is equivalent to, again, according to the Faraday's law of electromagnetic induction, right? So taking ratio of 1, can I consider this is equation number 1? Can I consider this as equation number 2? EP by E of S, that is equal to, right, NP whole divided by N of S. This is the first equation we are going to get from the transformer, right? Now, on the both of these sides, right, on both of these sides, we can say the product of EP, IP, that is equal to ES, IS. So EP by ES, that is voltage across the primary and secondary, that is IS by IP. So same again, we can write it here as IS by IP. This is only the equation that we are going to use into the transformer, the most important one, right? The most important one into the transformer, right? The most important one into the transformer. Okay, so when to just note this down, you can note this down. Okay, that's it. That much time is enough. Now, the question states that in a transformer, the number of the turns of the primary coil are, 140, and that into the secondary coil, right, are 280. Cool. The current into the primary coil is 4 ampere, right? What will be the current into the secondary coil? Great. Okay, and from this we are going to define whether it is a step up or step down. Okay, so now V by primary, V by secondary, N by primary, N by secondary, I by secondary, I by primary. These two equations, right, we are going to compare this two part of the mathematical expression, right? So we are finally going to get it as NP by N of S, that is IS by I of P, right? NP is 140, NF is 280, current into the primary is 4, and this current we need to calculate. So I, that is equal to 140 into 4 whole divided by 280. I, it is going to be 2 ampere. This is going to be the perfect answer for this specific question. Right, this is going to be the perfect answer for this specific question. Right, yes or no, boom, boom. Right, so this is what the transformer is all about. Now, an inductor of the inductance L and resistor of the resistance R are joined in series. They are talking about the LR circuit in series and connected by the source of the frequency omega. The power dissipated into the circuit is what? Faltu question. So I think this will be the homework from my side. Today, 2 homework based question I have given. So students, it was all about the alternating current, and soon we are going to come up with the EM waves and the wave optics in the sequential manner. Okay guys, that was enough for today. I think it's time to go, right? This is your own physics educator Indrajit Singh signing off from the desk. Bye bye, Sat Sri Akal and Namaste from my side. Bye everyone, stay at home, stay safe, stay healthy amidst this pandemic, and take care. Bye.